Hello, so today we are doing this problem called minimum height tree. It's a medium type problem on Leetcode. It's a very popular problem, so let's get to it. So the problem says for an undirected graph with tree characteristics, we can essentially, let's just remember that it's an undirected graph, and we can choose any node as the root, and the result graph is then a rooted tree. So when we choose a node as the root, then the tree, so basically tree characteristics here, let me just explain that a little bit. That means that it doesn't have cycles, because it has cycle, then that's not a tree, and it has n-1 edges, because as soon as it's had more than n-1 edges, it's no longer a tree. So those are the two tree characteristics, and it's an undirected graph. And we can choose any node as the root. The result graph is then a rooted tree among all possible trees that we can get by choosing any node as the root. Those that have the minimum heights are called the minimum height tree. And remember, the height of a tree is the length of the longest path in that tree, right? And the longest path, I mean from the root to any leaf in the tree. So given such a graph, we want to write a function to find all the minimum height trees, but essentially what we want really here is just return the root labels, which are here the nodes are labeled from 0 to n-1, and so we need to return the root labels. So for example, we can assume here that there are no duplicate edges, all that stuff. And here, for example, we have this graph with tree characteristics that is, if we root it at 1, then that's the minimum possible we can get, because if we root it at 1, that means the length here is just 1 for each. From the distance from each node is just 1. However, if we root it at 0, then the furthest distance here is 2. So that's not the minimum one that we can achieve. The one that can achieve for us the minimum height. And so for this example, if we take 1, we are going to have the height be 3, because remember, the height is the longest path from a root to a node to a leaf. And so the best we can do for a height here is that we can make the root be 3, and then at that point the longest path from that 3 to any leaf is 2, which is from 3 to 5. And for 4, if we take 4, the longest path or the height would be from 4 to 1 or to 0 or to 2, which is still 2. So these two have like the same height, which is 2, so we return them. And so this is the problem. Now let's think about it a little bit and see how can we solve it. So to solve this problem, first I'm just going to give a couple of things that will help us solve it in an easier way. So there are a couple of concepts with trees and graphs. So for a tree, there is something called center of a tree. What is that? It's kind of similar to the concept of root that the problem is describing, and that's just, it's a property on a tree. I'll define it in a moment, but we need another concept called remoteness. What is remoteness? It's remoteness of V. So V's remoteness, a vertex V's remoteness is its distance from its furthest node. And so this is kind of equivalent to, if we take V as the root of the tree, like if we root our graph at V, then let's call this R. Let's call this R of V, like a function. So if we take V as the root, of the tree, then the height of that tree is equal to LV, because essentially the height of the tree, as we said, is the longest path from the root to the furthest leaf from that root, right? Because that's the longest path, literally. It's the path from the root to the furthest leaf. So that's essentially the height, and so that's exactly the remoteness, is its distance of V from its furthest node. And so what is the center? Center of a tree is which is equivalent to the minimum height root that the question is asking, and that is just the a node that minimizes remoteness that we just talked about. And that's what we are looking for. We are looking for the nodes, can be one or multiple or two actually here. We are looking for the node that minimizes the height if we take it as the root, right? And so that means the height is the distance from the furthest node. So it's the node that minimizes the remoteness of basically of all the remoteness of that. So it's the node that if taken as root will have the minimum remoteness possible, right? So those are the concepts that we are dealing with. And now let's think about how can we find it. So I have some drawing here. Let's just see it for a second. So here we have the example that we have, the first example here. And so you can see in this drawing here, the node 0 has remoteness 2 because its furthest node is 3 or 2, and the distance is 2 edges, so it's 2. For 1, it's just 1 from each one of them. For 3, the distance is, the furthest node is 0 or 2, and those have remoteness 2. And same for 2 here. And so the one with the minimum remoteness is the node 1. So that's our answer, right? That's the one that if we pick as the root will give us the minimum height possible, because the height would be 1. Now if we take the second example, which is this here, if we take the second example, which is this tree, the same as this one, I just annotated it with the remoteness values. You can see here that we have, for 1, the remoteness is 3 because the furthest one is 5 and the distance here is 1, 2, 3. Same thing for 2 and 0. But for 3, the remoteness is just 1, 2. The furthest node from it is 5. For 4, the furthest node from it are 0, 1, and 2, and all of them have distance of 2 from it, right? So we can see 3 and 4 have the same remoteness value, which is 2. And so these two, because they both minimize the remoteness, as we said here in our definition here of the center, they are both a center. And so what you can notice here is that we can have at most 2 centers. So our solutions for this problem can have only 1 or 2 centers. They can't have more. And in what case we can have 2? So you can see here we have 2 because the longest path is because the longest path is odd, which is 3 here. So we have 2 in this case. Here the longest path is even, so we have only 1, right? And so that's just something that you can explore while solving this problem. And so we can see that there are at most 2 centers or roots, MHT roots. Now, a couple of concepts that we need to other concepts that we need to define just to be able to understand the solution to this problem, which are so a degree of a node is just the number of nodes incident to it. So basically what that means is that for an undirected graph it's those that are in the adjacency list of that node, right? So that's one thing. And then also a leaf has degree of 1. Why is that? In an undirected graph, of course. In an undirected graph. Because usually if it was a directed graph, then it would have 0. But this one here, the 1 is coming from the parent, right? from the parent. Because indirect graph, we add each node participating in the edge to the adjacency list of the other. And so the parent gets added to the adjacency list of its child, and the child gets added to the adjacency list of the parent. So any node that has a degree 1, that's for sure a leaf, right? We have also this concept called a path graph. What is a path graph? Path graph is it's a tree with 2 or more vertices that don't have any branches. So basically there is no node that has 2 children. Every node has just 1 child. Any branches. Okay, so let's see maybe an example of that here. So you can see here this basically this thing that I'm circling here, that's a path graph, because basically it looks like this. It's you have the node, and then you have the path like this, y, and you can imagine it like a path down instead, like this, because if it was a tree, so they're like this. And why? There are no branches, so there is no other node in this side, for example. So every node has only 1 child like this. Now this basically, if we take this one, this is a simpler case. So this is a simpler case. And this is like a very useful tool when designing an algorithm, which is usually sometimes goes by simplification, simplify and concur. So basically, take a simpler example and see how would you solve it. And so for something like this, how would we solve it? How would we solve it to find the root, the center that minimizes the remoteness? If we take something in the middle, so depending on if the path is like has length odd or even, if it has length even, then we will find the center in the middle. If it has length odd, then we will find 2 centers like this, right? 2 centers that can because both minimize the height, which would give us basically the same case as we had here with this where there is a tie like 3 and 4 here. Now with this case, how can we solve it? The simple way to do it is just take 2 pointers, P2 and P1, and move them like simultaneously at the same speed. Keep moving them, and at the end either they will both meet, so they will both, you'd have P1 and P2 at the same place when if the length is even, or you would have them like this, right? And so basically what we will be doing, and if whatever the case, either they meet or they are one edge apart, then we stop, and those 2 nodes or 1 node are the center. And so the solution for this case, for this simpler case, is take 2 nodes, take 2 pointers in the edges, or in the at the starting 2 pointers, P1, P2, starting at the leaf on the 2 sides of the path graph, and move them at the same speed until they meet or they are 1 distance apart, 1 edge apart. Then return 1 or 2 nodes they are pointing to. And so we have that solution for the simpler case. Now what can we do? This, if you think about it, we can just generalize this. So we take a simpler case and then we generalize it to a more complex case. So in our case, we don't have just this path graph, we have multiple, there are branches. And so generalize the solution, which is just put multiple pointers instead on every leaf, basically on every leaf in the graph, and move them at the same speed. And whenever two pointers meet, so let's just call this 1, and then 2, so 2 would be, so first we'll have multiple pointers on every leaf in the graph, and then step 2 we will move all pointers at the same speed, and then 3, whenever two pointers among these at the same speed meet or are at one distance apart, one edge apart, then keep only one of them, and keep doing this until there are, and keep doing that, basically keep doing 1 and, well, 1, 2, 3, until we have only 2 pointers, because until we have only 2 pointers, and that means we have found our centers, because we can have only 1 or 2 centers like this. And so so when there are only 1 or 2 pointers that are at the same node, or again 1 edge apart, then return the nodes they are pointing to. So we are doing the same thing we did with one simple graph. Just first we start out with all of them, and then we keep reducing until we get just 2 nodes that will give us the 1 or 2 centers. So one thing we can say about these 2 pointers, let's call them pk and p sub k and p sub k and p sub l. So what can we say about these 2 pointers? Since they are the 2 last ones, we can say that these 2, pk and pl, are in the longest path, right? Because if otherwise they would have met sooner, and they would have been made to be 1 instead, right? So these are in the longest path, right? Which means that if we take the nodes, their nodes as the center, we will minimize their mootness, because essentially it's the longest path. So whenever we take the longest path and we put the center there, that means we will have, because if we don't do that, that means we will have, if we take one with the smaller path, then that means those would have a height that is bigger, because they can go all the way, because in a tree you can do something like this. You can go from here all the way up, and so go from any node and go all the way and traverse the longest path, and then have more than that. And so the right strategy is to go to the longest path and just divide it by 2. Divide that longest path to get the minimum height. I hope that's a little bit clear. And so for our implementation of this solution, now let's think about the implementation of this idea. And so for this implementation, our pointers, well, I'm just going to call them leaves instead, because that's what they are, right? We start them and we put them at the leaves positions. And every time we advance a pointer, so let me just show the example I have for that. I think it's something like, yep. So what we'll be doing is something like this. So we have, let's say, this graph here, the graph that I'm pointing at. And so we will take the leaves first, and then to move, instead of just moving a pointer, because that would be hard on a graph, we are just going to remove them, or consider them removed. And so when you consider them removed, what does that mean? That means that the degree of the nodes connected to them become minus 1. Or at least we remove this node from the adjacency list of this one when we remove it. And so when we remove all the leaves, we will end up with these two. And so in this case, we already found our solution. It's the centers are these two, because as soon as we have 2 leaves, that means we are done. For this one, we will keep removing the leaves. And so we'll remove these leaves, and then removing them means the adjacency list of this node has one less, this one gets removed from it, and this one gets removed from it. And so we will end up with only these. And so we'll have these, we'll remove the leaves again, because it's still not 3. We still not have 3, we still not have 2, we have 3 here. And so we remove these 2 leaves again, and now we end up with 1, which is less than or equal to 2. And so we are done, and we return this as the center. And so the strategy here is, the fact that we are kind of removing leaves, that's kind of our way of advancing our pointers. And saying that 2 pointers meet in our case here is just saying that, okay, we have only 2 leaves left, or we have only 1 leaf left. And so that's how we are going to do the implementation here. And so we are doing this with BFS, because BFS allows us to do level by level. And so the first level will move these leaves, and then the second level, so let's take actually this example. So the first level will move these leaves. The second level traversal will move these leaves. And so it's kind of BFS, but we are not going level by level, but we are going by leaf, and then leaves again, and then removing these until we end up with only 2 leaves or 1 leaf. And so that's the idea. So let's get started and implement it. Okay, let's just get started and implement. So what is, first, before implementing it, what do we think the complexity is of this? So we will keep removing leaves until we have 2 or 1. So at most we will remove n-1 leaves, or nodes in this case. And so the time complexity here is just O(n), such that O(n) is the number of nodes. And the space complexity is the space complexity of BFS. And since we will keep storing the leaves here, we'll keep removing leaves and finding the new leaves. So also the space complexity would be at most the number of leaves, which would be at most O(n), right? So the space complexity also is O(n). So let's implement it. So to implement this solution, we need, of course, the adjacency list, so that we can be able to remove. Once we remove a leaf, we can remove it from the adjacency list of the nodes connected to it. And so to do that, we are going to have an adjacency list constructed as a set or a list, whichever is easier. Both are fine. Since there are no duplicate edges, we can afford to have that set. And so, and then we are going to go through the edges so that we can add them. And this is an undirected graph, so we are just constructing the adjacency list. And so adjacency list of u are going to append v, and for v we are going to append u. And now we are going to have our leaves. The first set of leaves, which are these ones here that have degree 1. Remember, we said a leaf has a degree of 1 in an undirected graph. And so, and which is coming from the parent because of this here. And so our leaves are going to be I for I in range of n-1, in range of n, if the degree is 1. And what is the degree? It's just the size of the adjacency list. So the adjacency list of I should be equal to 1. So these are the leaves. Now, what did we say is our stopping condition is if we have, so we have at most n, we have at most 2 centers, right? That's what we said here. We have at most 2 centers. And so we'll stop when our n becomes just less or equal to 2, because that means we are either in this case or in this case, right? And so what we are going to do is we are going to do while n is so this is still BFS. You can see here that BFS can be different than the usual vanilla BFS that we do. So here our stopping condition is while n is bigger than 2. So whenever it's less or equal to 2, that means we are done, we found our centers. And so we need to subtract from n the length of leaves, because these we are removing them, and so we need to subtract them from the number of nodes in our graph. And so the length of leaves, and then we are going to construct the list of new leaves, right? And these are the, once we remove these leaves here, we will end up with this new graph, and so the new leaves are this one and this one. And so we are going to construct a list that will keep them, that will keep track of them, basically, because every time we remove a leaf, the one that became with the degree 1, that's a new leaf, right? And so this is our new leaves, and then we are going to go through each leaf and see removing it made which node become a new leaf, right? So in leaves, then we are going to take first so it's a leaf, so it has only one adjacent node, right? And so that's the parent, so let's just call it G, and the way we can get it is just by going adjacency list leaf, and since we are removing the node, so we can just say pop, so that leaf will have no longer the parent as in its adjacency list, so we can just pop it. And then we are going to take the adjacency list of J, which is the parent. Since this one is removed, so it's no longer, this one is removed, so it's no longer part of its adjacency list, so we need to remove it. And so we would say remove leaf, right? And now we will check if adjacency of J became 1, because we removed the leaf. Did it become 1? If it became 1, then it's a new leaf, which is what happened in this case. But maybe it's not, because maybe there is another node connected from this side. So we are going to check, and then if it is, we are going to add it to the new leaves. And then after this, so we traverse all the leaves. After this, we are going to assign, for the next iteration, we are going to assign to leaves these new leaves that we just put. And so we didn't alter leaves here so that we don't mess up this for loop, so that this for loop doesn't go through the new leaves, right? And now what should we return? So we should return whatever is left in leaves, because when n bigger or equal to 2, that means whatever the last leaf, like in this case, or in this case the last 2 leaves, that's the solution. So we can just return this. And that's about it. That's pretty much the solution. And so why is it BFS? Because we are going through the neighbors, adding them kind of to level by level, except our levels here are leaves instead of the normal tree levels. And that's pretty much it for this solution. And so let's run. Okay, it's add. So here actually it's not the adjacency of J that is equal to 1, it's its length. That's what we mean by a leaf, which is the same that we did here. Okay, so that passes there. So you can see here for the time complexity, you can see here that we keep doing n until n is less than or equal to 2, we stop. And every time we subtract the number of leaves. So you can see that at most we will do O(n) operations if like on every iteration we remove just one node as the leaf, and that may happen in this case, then we have O of n. So the time complexity is O of n. What is the space complexity? So the main things we are using are this adjacency list and this leaves. The adjacency list is at most of the number of edges, and those are in -1. So the graph here is at most space complexity of O of 2e, and since this is a graph with the tree characteristics, so we have at most n-1 edges, or we have n-1 edges. So this is pretty much O of n. And then for these leaves, we keep adding only the leaves. So we keep adding only the leaves. So at most it will be the number of nodes in the graph. And so this also is O of n. Even combined with the new leaves, both combined, it's just O of n. So the overall space complexity is just O of n here, which is what we said here. And that's it. So let's first run this, submit it, and see if it passes. Okay, we have one wrong case, which is if we have one in an empty list. And in this case, we should return 0. So actually, this one we can just handle by checking if n is equal to 1, just return 0. Okay, so submit. Okay, so that passes. So this solution was using BFS and using this trick of removing leaves. This is a useful trick. Sometimes also it can solve topological sort. I have a video just before this one that uses it to find if there is a topological ordering. The problem is called course schedule. So you can take a look at that. Now we can solve this actually with a different method. So let me just explain that. I'll keep this in a. So the other way we can solve this problem is using this concept of max path. So what is the longest path? So if we find the longest path, let me just put back those something that we need. So we need this. So if we find the longest path, right, then we can just take the middle, or if the length is like if the length is odd, then we take the two middle points. That's what we said. If we have the longest path, that's a way to minimize the remoteness here and to get the minimum height, right? And so the way we can solve this problem using that is we can just, how can we find, so we need to find the longest path and then just take the middle one or two nodes depending on whether it's even or odd. And so how can we do that? So first, to find the longest path, we can just select any node x. It's kind of called the greedy approach in a way. And so we can select any node x, and then 2 and consider the root. And then the second step, we do a DFS or BFS. I'm going to do DFS in this case, but both work. And so, and find y, which is the node with that achieves the highest RV, right? With the highest RV, the highest Rx, basically the highest remoteness from x. So it's the node with the the node with the longest distance from X, right? So, and then the third step, we will let Y be the new root and do another DFS or BFS to find the node with max error of Y. So same thing, the node with the longest distance from Y at this point. So, and do another bit to find the node, let's call that node Z, right? And so now this means that the path Y to Z is the longest path. Why is that? Let's just, so because if we have a tree like this and we pick any X as the root, let's say we pick this X as the root. And so basically with this, I'm just, this here rectangle, triangle is just modeling that there is a subtree that can be large, that can be small, we don't care. But in our solution here, we'll first pick an X value, there is any nodes in the tree, and then we are going to do a DFS or a BFS to find Y, which is the node that is furthest from X. Let's just suppose this subtree was really long, and then Y was somewhere here. Then we'll do another BFS that finds the node that is the furthest from this Y. And so a tree, remember, is all connected, and so we can go all the way from here, pass through the root, this red line here, until Z, until we find the Z here. We can do this with DFS. So this here is our longest path. Whatever, if we take anything else you can see in the representation, it won't be the longest path because all the tree is connected, right? So that will give us the longest path. And then once we find this longest path, so since this is the longest path, just take its middle one or two nodes, and that's the solution, and we are done. So yeah, that's it. So let's just start coding it up. So we said first we need to construct the graph, right? We need to construct our adjacency list as we did earlier. We can use the same set as we did, but I'm just going to use default dict with set, which would be the same thing as doing, this is the same thing as doing set for a range of n. I just like to give you a different implementation so that you can, whenever you read new code, you can understand it. And so we are going to go through the edges and put them in the adjacency list. And so adjacency of u, we are going to add v, and for v, we are going to add u. And now we are going to do the steps that we said, right? Select any node x as the root. So I'm going to select x as 0. And so this is step 1. And then we are going to find the max, do a DFS or BFS to find y, which has the highest Rx, right? Or the nodes with the longest distance. Let's just call it the node with the max path. From X. So that would mean max path. We are going to find max path from X to and since I'm going to use DFS and don't want to do visit the same, just the normal BFS, we have visited set, right? So that we can keep track of the nodes that we visited. And now we are going to find that path, and we are going to put it in a list like this. And so let's just write the signature of our max path. So it takes a node, let's call that v, and the set that is visited, and does DFS to find the max path. We'll write that later. And then, so this is the second step. Then our third step is we take the y as the new root and do another DFS, BFS to find z, right? And so our y is going to be whatever path we returned. We will write our BFS in a way so that so that y is at the first position 0. I will show how later, but this is the third step. And then let's just make this 4th step, and then this is 5. So do another DFS or BFS to find the node Z that has the longest distance from Y, which is the node with the max path from Y. And so that would be max path from Y and a new set of visited so that we can find it. And that will give us another path that contains Z. But this path is the longest. So Z is at position path 0, but we don't really need Z here. So Z would be at path 0. And then now we just take the middle, right? So we just return the middle, and there is a nice trick to find the middle of this path, which it can be either 1 node or 2 nodes, because I will show later why, but we can do that by just doing m minus 1. So let's take m as the length of the path. So it would be m minus 1 divided by 2, and then m divided by 2 plus 1. So why is this? So because let's take an example. If the path length was 4, that means that this here, what would it be? So this would be, because m minus 1 divided by 2 is going to be equal to 4 minus 1 divided by 2, which is 3 divided by 2. And so let's just write this in Python and see what this gives us. So 3 divided by 2, that's 1, right? And then m divided by 2 plus 1, that means 4 divided by 2 plus 1. So let's write that here again. So 4 divided by 2, that's 2. 2 plus 1, that's 3. And so this is 3. So our path is actually, so this is, our path is that we said here. The first one, which is this one, it's 1. And the second one, which is this one, that's 3. So this is essentially, what is this? This is just, in a list, that's just path of 1 and path of 2, right? Because if my path is, let's say, 1, 2, 3, 4, so the length 4, right? If I do path 1, 3, I should get just 2 and 3, right? And that's exactly what it should be, because both 2 has distance. If this is the path, it has distance 1 from here, from its furthest, no, it has distance, sorry, of 3 from its furthest node. 1, 2, actually 2 from its furthest node, and this one has distance of 2 from its furthest node, so they have the same remoteness basically. And so that's the case of when n is odd. So this is case when m is even, sorry. And so when m is even, we verified that this formula gives us the right thing, right? So now let's verify that when when m is odd, that this formula gives us the right thing. This is a nice trick to remember to use whenever you have something that can give only 1 or 2 values, depending on the, in a list, of course, depending on the on whether it's the length is odd or even. Now when m is odd, let's take an example. Let's take, for example, 5. In that case, the path is still this, and so what is the value of this? So in that case, this here is equal to 5 minus 1 divided by 2. So that's like just 4 divided by 2, so that's 2. And the case of m divided by 2 plus 1 is equal to m is 5 divided by 2 plus 1, so let's see that, what is 5 divided by 2 here, that's 2 plus 1, so that's 3. So that's 3 actually. So our path, this path here, is just equal to 2 to 3. And in this case, this is in Python just path 2, right? Because, again, let's just add to our path so that its length is 5. And now if we do path of 2, path of 1, 2 to 3, that's just this value here at position 2. And yeah, so we know that this works. And so now let's just write our DFS that find for us the max path using DFS. So this, I'm going to use DFS. You can use BFS also. And so the implementation of this, first we need to add to the visited set, we need to add V, right? And then for all neighbors, we are going to visit all neighbors to obtain the max path that is coming from all neighbors. So the max path among all neighbors, that's what we want. So let's take first all paths of all neighbors. So that would be max path starting from that neighbor, let's call it, and then let's call it W, the neighbor. And then we will pass the visited set. And what is W? It's the neighbors of V. So that's the adjacency list of V. But we don't want to visit a node that was already visited, a neighbor that was already visited, so we need to check that it's not in the visited set. And now we want the max path among these. So our max path that we are interested in, that's the max in paths. And what is the key that we will be using? It's the length. Python, you can pass a key so that it compares using that. So we are comparing all paths using their lengths so that we can get the max path. And now once we get the max path, we will add the node here to it. And this is what allows us to have at the end y at path 0, because we'll keep adding to the end. So the last one would be added to the end, and so that's why it's y. It's at that edge. It's at that end of the path. And at the end, we can just return that path. And yeah, that's pretty much it. And so now we did all our steps, 1, 2, 3, and then this was step 4, and this was step 5. So yeah, that's pretty much it. Let's run it and see. So we have a problem with this max. So paths here may be empty, right? That's the problem, because if we do, so here it's saying an empty sequence. It cannot accept an empty sequence, because if we do max of something like this with key is equal to length, then we have a problem. So the way around this is to just say, or if it's an empty list, let's just give it a list of empty lists so that it can return us just an empty list. And so the way we are going to do that is just avoid that problem just by doing this. Okay, so we have the same problem of n equal to 1. Let's solve that. Let's just solve that by doing n equal to 1, return 0. Okay, now let's take this to make sure that this works. So let's take 4 and this. Okay, so we still have a problem there. So we have an issue somewhere. It's not just the first case. And this is path. So we add, let's verify our max path. So we add to the visited set, we take the max path among all neighbors. And we take it only if it's not in the visited set. And then we take the max path among all paths using the key length. And we append v after that, and we return that path. Okay, that seems correct. Let's see our adjacency list. So we have uv, and then we add u to v and u to the adjacent v to the adjacency list of u and u to the adjacency list of v, so that's good. We do the first path from 0, and then y is path of 0, and so we do that, we get a new path. Yep, the problem maybe is just the parentheses of this, I think. Maybe it's doing m minus 1 divided by 2. Yes, that was what it was doing. And let's go back to the case that we had a problem with earlier. Okay, so that case passes. Now let's just try on this with value 6. Okay, so that passes. Let's submit. Okay, so that solution passes. Yeah, that's it for now. Yeah, so sorry, I forgot to say the time complexity of this. So this is DFS. So the time complexity is usually just we are doing DFS here 2 times. So it's 2 multiplied by v plus e, so it's around v plus e. What are both v plus e? Our v is just n. Our e is n minus 1, and so it's kind of O of n plus n minus 1, so it's around O of 2n, so it's actually just O of n. That's the time complexity. The space complexity is also we are having paths that contains the longest path. We are having 2 of them, so at most each of them is n, so both are n. So this was the this was the time complexity. And so the 2 paths that we are using here both also are at most n, and so we have also O of n in terms of space complexity. Yeah, so that's it. See you next time. Bye.